Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about a very important statistical test called students t-test. So I hope the screen is visible. Let's set up the agenda. So this is one of the many statistical tests which we use for hypothesis testing. Okay, so the agenda will discuss about what is t-test and the underlying distribution of the test is t-distribution. We'll discuss about this, and then we'll discuss about the two types of the most common uses of this t-test. One is one sample t-test, another is two sample t-test, and we'll see examples, one example each for both of them. Okay, so let's begin. The first thing, what is t-test? Okay, what is t-test? So this is another one of the many tests for doing hypothesis testing. Okay, and this is used to determine if there is any significant difference between means of two groups. So either it can be the population mean versus the sample mean, or means of two groups. And if we want to compare the means, then we go for t-test. We use z-test also, but why is this important? So when we have number of samples is very small, that's where it shines. It is useful. That's where it is so useful, and it was designed for that. When the number of samples is less than 30, anything greater than or equal to 30 was considered large when the computing capacity was very low, when these algorithms or these tests were designed. So anything less than 30 was considered as small, and for this t-test was designed for doing this. And there is one more thing, that since the sample size is too small, the population standard deviation is unknown. So there's another thing, that sigma or population standard deviation is unknown, not known. Because the sample is so small, computing standard deviation will be like, it won't give me the accurate information. That's why we'll introduce one more concept called degrees of freedom, which I'll discuss later. Okay, this is because the standard deviation, it won't give the correct picture of the exact variance in the or variability in the data. It won't capture because of small sample size. Okay, that's where it's useful. And the another thing is that the underlying distribution is called t-distribution, or specifically there's a name called students t-distribution, and I'll discuss about why the name student also. So the distribution, underlying distribution is student t-distribution, but the name students t-distribution. So let's discuss about the distribution, the students to t-distribution. What is this distribution about? So all right, students t distribution. So this is the short form, B. Okay, that's what I use. So this student name came because of the mathematician who invented this. So when he published his paper, the mathematician's name was, or statistician's name was William Gossett, but he published the paper under the pseudonym student. That's why the paper, okay, where it was published, it is named as students t-distribution, because it was invented by a mathematician called William something Seeley Gossett or something, William Gossett. But for publishing the paper, okay, to publish the paper, he used the name, a pseudonym, an alias. Under this name, student, he published the paper, and that's why this distribution or this test got this name, students. So that's the history behind this. Okay, and what does it do? What is the t-distribution about? So this is a generalized normal distribution. So we are very familiar with the normal or the Gaussian distribution, and it generalized that for small samples. So it generalized Gaussian distribution, generalized normal distribution for small sample for n less than 30. Okay, and there are some features. It is symmetrical around 0. So it is the same bell kind of curve which is symmetrical around 0. Okay, kind of similar. So this is your mu, and but the tails, these are thicker than a normal Gaussian distribution. The normal Gaussian distribution will have a thinner tail. The tails are thicker, and also the thickness of this tail is determined by another thing called degrees of freedom, which we'll discuss now in some time. Okay, so this is the saying that it is a generalized normal distribution which is symmetric around 0, and it is but has thicker tails. So I'll write it. It has thicker tails. The tails here, these are thick. The area under the curve, this is thick. This is a bit thick. Okay, normal distribution will be thinner. It will come closer to the line. That's the difference. Okay, and since the sample size is small, so that's why we cannot use the sample standard deviation as the population standard deviation. And to estimate the variability in the data points that we have in the data set, we use something called degrees of freedom. And the degrees of freedom, it measures the number of independent data points present in the data set, using which we can do a good estimation of the variability in the data or the variance in the data. That's what degree of freedom is. So let me tell you what is degrees. This is the same concept is borrowed from physics also. Okay, in physics also you will have degrees of freedom. You will see in when we were doing adiabatic or isothermal process. Okay, PV gamma equal to constant is equal to constant for adiabatic, or P1 V1 equal to P2 V2 for isothermal. There also we had degrees of freedom, if you remember. Just an old physics revision. But these concepts are borrowed from physics. So what does it mean here? For example, for understanding, say for example we have 10 observations or 10 data points. We have 10 data points, and the sum of those data points is equal to 50. Okay, understand? So I can have here the sum of first 9 values can be anything. The sum of first 9 values, or if I take one by one, sum of arranged in any order, not in ascending or anything, but sum of first 9 values can be anything. Can be anything. Anyways, it will be less than 50. But the 10th value, that cannot change. 10th value will be fixed. Why? Because it can only be equal to the 10th. Okay, these are the 1 to 9. The 10th value or the 10th data point can only be 50 minus sum of these 9 values. Are you getting it? The 9 values can change anything. They can have any sum. They can come to any sum in any order we take. But the 10th value will be fixed, and it will be dependent on the first 9 values. Whatever the sum of 9 values, and the remaining value can only that value the 10th data point can take. This is 10th value or 10th data point. I hope you get the point. So 9 values can independently change, but the 10th value is dependent on the other 9 values because the sum is fixed here. And that's why the degrees, the number of independent pieces that can be changed independently here would be 10 minus 1. So I'll write degrees of freedom is equal to 10 minus 1, that is equal to 9. I hope you get it. And that's what degrees of freedom means here. That only 9 data points can vary independently to give any sum here. But the 10th data point will be dependent on the other data point because the sum is fixed. The sum is 50 because the data points will have some fun. I take the values from any order. So the 9 can change any, and I can get the sum as 45, 46, 41, anything. But the 10th one's value will depend. So whatever remains, its value will be dependent on the what first 9 values I picked. And that's why my degrees of freedom would be 10 minus 1. So the degrees of freedom is defined here as n minus 1, where degrees of freedom is equal to n minus 1, where n is equal to number of observations or number of points, or the sample size simply. That's the number of observations, right? So my n would be equal to the sample size, the number of samples I have collected. I hope degrees of freedom is clear. This is very important concept that will come whenever you talk about t-distribution, and other places also you will see degrees of freedom. This will keep on coming. Okay, so let's move. Once this is clear, so we have this. So let's see the distribution. Okay, so the t-distribution, how does it look like? How, if you vary the degrees of freedom, so what will be the t-distribution like? So let me show you the Wikipedia. So students, T distribution wiki. Take me to the wiki. And let's, yeah, this is the PDF of this. You see, this is similar to that. Let me take a screenshot of this and we'll discuss. This variable like V, this is your degrees of freedom. This is the symbol. Okay. Let me paste it and let's come back. Okay. So this is your, so if you see, this is similar to your bell curve, symmetric around 0. So this is your central point, and this is V. This is your degrees of freedom. Okay, this is the degrees of freedom. So as V changing and as V tends to infinity, this will tend to a Gaussian. So as this V, this is degrees of freedom, tends to infinity, this T distribution will tend to a normal distribution. That's the property. Okay, as this symbol kind of V, this is the idea. As it tends to infinity, your T distribution will become a normal distribution because you have a lot of data points now, and this n sample size will increase. So for large sample size, automatically the whole problem was because sample size was small, and as n tends to infinity, this will become a normal distribution. No problem. That's intuitive. Okay. I hope T distribution is clear now. Now let's move to the test. So what are the types of t-test? I've told you earlier there are 3 types, but mostly 2 are very popular that we use, and I'm going to discuss that in detail with example. But I list down the types of t-test. There are 3 types. So there are types of t-test are so one is, as I mentioned earlier, one is one sample. So everything is to determine mean. Okay, one sample. So one sample mean t-test. Okay, so if again, so this is for checking whether the sample mean differs from the hypothesized population mean. Okay, or whatever value I have. Okay, so this is a like sample mean differs from what is the hypothesis. Okay, whatever the hypothesis for the hypothesized value, whatever value we have for the population mean. So this is one value only, and there is a hypothesis that this should be the value, and we check against that. And the second one is 2 sample, where we compare means of 2 groups. Okay, here test whether 2 independent samples, those are coming from 2 different groups, independent groups, and if the samples differ. So this would be test whether 2 independent sample means differ. Okay, so these are the 2 which we are going to discuss. There's one more. I mentioned this in the earlier. There is a paired t-test. I won't discuss this about this. I'll just mention it. So this is to test whether a related sample differs. Okay, this is to test whether a related sample differs. Related means a related sample differs. Related means before and after change. So before something happened and after that event happened or some changes were done, if there is a difference in the mean, so we'll compare the same mean against some change before and after test. When we do, then we do paired t-test. Okay, but I won't discuss about this. I'll discuss about this and this. 1 sample mean and 2 sample mean t-test. Okay, so let's go for 1 sample mean t-test. So let me go to the next page. So I'll just write mean is implicit here. I'll just write 1 sample t-test. So 1 sample t-test, as I mentioned, this is for comparing sample mean is equal to a known value. Compare sample mean is equal to a known value, whether yes or no. Okay, that is the hypothesis, yes or no. Okay, whether it's equal or not. So what's the test statistic? So whenever we do a test hypothesis, these are kinds of hypothesis tests, right? So always we'll have a test statistic, and we'll have a formula for that, and this will be across multiple tests. So whenever we have any test, there will be a test statistic defined for that, and this is the test statistic for this one sample t-test is we say t is equal to sample mean minus mu, or whatever is the hypothesis, okay, and then the standard deviation by square root of n. This is your standard error also. So this is your sample standard deviation. This n is the sample size, and these are your sample mean, and this is your, you can say mu naught also. This is your population mean, or whatever the value, known value is there, population mean. Okay, so this is a test statistic. It is defined for all the tests. This is how the test is defined. There's a derivation for this also, but I won't go into that. So just know this is they're very common. Then they have a pattern. Always whenever we compare means, so there will be a mean at the top, and there will be some form of standard deviation in the denominator, because the units of whatever is the unit of the mean and the unit of standard deviation, they will be same, and this will be standardized. So finally it will become unitless. Standardization means making it unitless. There's no unit in that. Okay, and all of the test statistics, what we'll see, you will see it in this form only. There will be some mean, difference of some mean that we are calculating, and there will be some form of standard deviation at the denominator. Okay, just keep this in mind, and all those tests will start making sense. They have a pattern. Okay, and the degrees of freedom, as we calculated here, what will be the degrees of freedom here? Degrees of freedom for one sample t-test. This varies. Okay, this is n minus 1. Okay, let's do a quick problem to understand if you have understood this. So let's check that. So there is a software developer, an API developer, who claims that he has improved the algorithm. He has come up with a new algorithm which improves the API response time by 100 milliseconds on an average. So, and he has developed that and given it to the tester to test it. Now the tester is verifying his or her claim whether the API's average response time is 100 millisecond or not. Okay, or it is greater than 100 millisecond. So a developer has developed and the tester is testing. So what is that tester? What is the problem? A developer claims that the new algorithm, whatever he has done, new algorithm improves API response time by say 100 millisecond. Okay, on an average. So that's the mean. And the tester, or whatever the test suite, whatever they verifies this claim. So this is kind of hypothesis testing, that there is a hypothesis and the tester will, so he or she will use this one sample t-test to verify this claim. Okay, so let's see what data we have. So what is the true or reported mean, or the known value? So the true mean, or whatever is the mean, average, whatever they have reported, this is your mu is equal to 100 millisecond. What other information we have? We have sample mean. Sample mean after so their sample size, the tester ran this experiment say 20 times and found some average out of this. So there will be sample mean of all the API responses. So this will be your x bar, and that was 115 millisecond. And then there was sample standard deviation. Okay, so this is your S, and this was found to be 25 millisecond. Okay, so this data we have, this is your input. After taking 20 samples, 20 times running this test, they found that the mean is 115 millisecond, and the standard deviation of this these samples, 20 samples, is 25 millisecond. And now let's verify the claim using the standard hypothesis testing framework. So first of all, what is the first step? We make our null hypothesis, and we declare what is the null hypothesis and the alternate hypothesis. So what is our H0 here? H0 is always that everything is same. Okay, so H0 is that your sample mean is equal to the known mean. So nothing has changed, everything is same. Okay, so that is you accept that. Okay, this is 100 millisecond. But the alternate hypothesis is that no, the sample mean is greater than mu. So this means that this is greater than means this is a right-sided or right-tailed test. Okay, this is greater than. We have discussed this in the hypothesis testing video. You can check that why it is right. If it is greater than, it will move to the towards the right side of the hypothesis. So this is your first step. Other steps also will come as it is. So we have our null and our alternate hypothesis. And now let's check the test statistic. So what is the test statistic here? So this says that this is x minus mu. So we have decided that we'll do one sample t test, and let's see the t observed. What is the value? So this will be x bar minus s by square root of n. You have this. X bar is 115. This is 100. S is standard deviation is 25, and then square root of n is 20. This is your 15 by 25, and the square root of 20 will go above. This will become here. This will become 3. This will become 5. So this is square root of 20 into 3 by 5. Square root of 20. Let's see. This QRT of 20. This is there into. Okay, so we'll do one more. 5. This is 3 by 5, right? So 3 by 5 is 0.6 into 0.6. So this comes to 2.68. 2. So this is equal to your 2.68. Okay, approximately. So this is what we calculated. So your t observed is 2.68, and we have this. Now we have to find. So what is we have found the distribution is t distribution. We know that. We'll see that. Okay, and now we have to find what is the significance level. Let's say this. So say significance level is 5%. So you have to find the critical value t alpha for 0.05. That is your critical value. Beyond this, if this is so, this is your, if you remember the hypothesis testing video, right? So this is it. So I have to determine what is my t alpha. Okay, beyond this, my area under the curve will be, so this will be your 5%. Your area under the curve will be 5%. So what is that value? We have found that t observed is 2.68 here. 2.68. So whether my 2.68, sorry. So whether the 2.68, so whether this 2.68 is here or here. If my 2.68 is less than the significance value, your alpha. If it goes in this region, if t alpha is whatever the value and 2.68 comes here, then I'll reject the null hypothesis, because the area under the curve, the p value will be less than alpha. Okay, and if it comes here, if it comes somewhere here greater than, okay, on the less than, on this side, then the area under the curve here, the p value will be greater than alpha. So I'll accept the null hypothesis. So how do we check what is the t alpha? For that, for each distribution there is a table, and let's see the table for that. So if you go and let's do Google search. I have done this already. If you go back and search t-test table PDF, you will get a t table. Then go to that table here, and then what is the degrees of freedom here? So we have 20 samples, right? So my DOF also we have to see. So it will be based on degrees of freedom. So my degrees of freedom will be equal to 20 minus 1, that is equal to 19. And my alpha is, significance level is 0.05. Okay. So this is your one tail. Okay. So here t is 0.05 here. If you see, that is highlighted. And if you come here and see degrees of freedom is here 1, 2, 3, 4, 5, 6, 17, 18, 19, 19. Here 19, and you see here at 0.25. If you see, this is the value. Here I have highlighted this in this row. 1.729. So your T alpha is, let me come back. Your T alpha is equal to 1.729. And this is, and this side the 0, it is symmetrical round mean. So this is your 0. And my T alpha is, T observed is here. that is equal to 2.68. So if you see the area under this is definitely, so this will be my p-value, that is equal to probability of seeing any t greater than equal to t observed. So my p-value will be less than 5% definitely, because the area under the curve will be less than this. So we reject the null hypothesis. So finally the conclusion, we reject null hypothesis, okay, and accept the alternate hypothesis. And what is the alternate hypothesis? That every average or mean API response time is significantly greater than 100 millisecond. So the developers claim is it's verified, and the testers found out that no, it is not on an average 100 millisecond, but it is significantly greater than 100 millisecond. I hope this is clear. Okay, now let's move to the second two sample t-test. Okay, so the next one is two sample, again it's for mean only, two sample t-test. So there are two types of two sample mean test. So first one is for, okay, so the first one is for unequal variance, means, so basically this is for comparing two samples, right? So this is for comparing unequal way, okay, for two independent samples. So we have two independent samples or groups, and we want to compare the sample means of that. Compare two independent sample means, whatever is the mean, but the variance of them is unequal. So each sample will have their own sample variance. So S1 and S2, they are not equal. That's there, and there are two chances, right? They can be equal also. So we'll see that next. So but when S1 is not equal to S2, the sample standard deviation, okay, this is S1 square. S1 is the standard deviation, and this is your variance. Okay, it will be the same. Okay, so are significantly different from each other. That's what we have to do. So what will be the test statistic? Again, I'll just go this. You should just know the formula here, and then we'll do a problem. It will become very obvious. So my test statistic would be t is equal to difference of the two means, as I mentioned, and there'll be some form of standard deviation in the bottom to normalize or standardize it, some scaling factor, and this will be equal to S1 square by N1 plus S2 square by N2. These are your sample means. These are sample standard deviation, and this is your sample size. Okay, but the degrees of freedom, the way you calculate here is this is also called Welch formula. Welch. Okay, so the degrees of freedom here, it is because the variance is unequal, the degrees of freedom calculation is a bit different. So we calculate, so this is given like this. Okay, so it is kind of V, sorry. Okay, so this is given by, the formula is S1 square. So S1, it is a bit different, S1 square by N1 by S2 square by N2 whole square. Okay, and then divided by S1 to the power 4 by N1 square into N1 minus 1 and S2 to the power 4, it is symmetric, N2 square into N2 minus 1. So this is how we calculate the degrees of freedom. So this is coming from, so this was given by a mathematician called Welch and Satterwhite. Okay, so but we know it as Welch formula. Okay, the second name is a bit difficult to pronounce. So this is the degrees of freedom, how we calculate it. Okay, so this is for unequal variance. So this is your mean difference by, this is your standard deviation of the first sample, standard deviation of the second sample, or the variance of first sample, variance of second sample, and scaled by their sample size. And then the degrees of freedom, we have a complex formula. This is generally computed separately. And the other second case would be that that equal variance. Both the samples variance is equal, that is s1 square is equal to s2 square. In this case, okay, in this case, what do we do? That we have a pooled variance now, because both are same. Now we create a pooled variance including their degrees of freedom, because the degrees of freedom is included for capturing the variance or variability in the data. How many independent data points are there which can be used for capturing the variance in the data. So this includes all those degrees of freedom also in this, and you will see the pooled variance formula. Earlier in the Cohen D, when we are discussing effect size, even there you would see a similar formula. Just go and check that. So I'll put the link of that video. So even in that video we have a similar pooled standard deviation. Okay, so pooled variance, here we have pooled variance. There we had variance and standard deviation are same. Standard deviation is just the square root of variance, so it is same. So this is given by s square of p, pooled. Okay, and this is n1 minus 1, okay, into s1 square plus n2 minus 1 into s2 square by sum of the degrees of freedom, n1 plus n2 minus 2. So this is like, if you read it, this is equal to n1 minus 1 plus n2 minus 2, n2 minus 1. So this is nothing but the sum of the 2 degrees of freedom for both the samples. Both have equal variance, so we can just add them up. Here also these are the degrees of freedom which are multiplied, and this is like kind of summation. So we have a pooled variance now, and this will be included in our test statistic. So what will be our test statistic? My test statistic in this would be, earlier we have written the test statistic, right? Yeah. Test statistic T is equal to similar x1 bar minus x2 bar, the sample means of the two independent different samples what we have, and then the pool variance will come out, and into 1 by n1 plus 1 by n2. Similar stuff. Okay, if you see, because this pool variance is common in both, it has come out, and 1 by n1 plus 1 by n2 remains constant. If you see in the same format, it can be written here also. x1 bar minus x2 bar by, if you put this sp inside the this one inside, this will become s square p by n1 plus s square p by n2. Okay, now you see both have taken the same form. If you see here, this was independent, and here we have the pooled variance including the degrees of freedom. Okay, and now here the degrees of freedom will become, here the degrees of freedom v will be equal to n1 plus n2 minus 2, that is equal to n1 minus 1 plus n2 minus 1. So that's what we have seen earlier in the one sample test also. So that's why it is coming like this. Okay, let's quickly solve a problem here and you will understand. So I have a question for you. So we have a AI team that wants to validate if the new ML model they have created, whether its accuracy is better than the existing or the old algorithm or old model, ML model. Okay, so we have an AI team and we have the data for each of them. Okay, AI team wants to validate, and they can perform a 2 sample t-test because these are 2 independent model data. Wants to validate whether if the new ML model's accuracy is better than the accuracy of the existing or old algorithm. Kind of A/B testing. That's what they want to do. So they have some sample around that. So they will have some sample size, and then they will have sample mean, and they will have sample standard deviation for both of them. So let's say we have new, let's say, and then we have old. Let's say this is B. Okay. So NA is equal to 24 and B is equal to 18. Okay. and the x bar a, this is sample. Okay, this is 91%, and this xb bar is equal to 88%. This is your accuracy. The old model is 88%, the new one is 91%, and the standard deviation for a is 4%. Okay, not a 4%, 4, and this is this is 3 only. Okay, this is the data you have, and then assumption is, we assume that the population variance of both the samples is almost same. So we assume that nothing is given. So assumption is that population variance population variance is of A is equal to, is approximately equal to A. Both are approximately equal. So since the population variance is same, we can use the second equal variance test. Okay, or standard or population or the sample variance. Okay, both are same. Yeah, the first one was unequal variance, the second form was equal variance. I'll use this test now. So this will be my test statistic. So for this I need to calculate the pooled standard deviation, and then we just put plug all the values in the formula and get the formula. This is just simple maths. So let's do it quickly. So before, this is hypothesis testing, so we have to go via the same route. So what is my null hypothesis? I use a different. Null hypothesis is that accuracy of new ML algorithm is equal to the old algorithm. Nothing has changed, status quo. So accuracy of new ML algo A is equal to accuracy whatever is equal to B's. Okay, B's accuracy. Simple. Nothing has changed. But HA says that, alternate hypothesis says that accuracy of A is greater than accuracy of B. Since this is greater, so again this will be a right tail test. So I'm just using the simple right tail test, so that to give you the intuition of the, if it is less, then you will go to the left tail test. Okay, if it is not equal, then you will do two-sided. Okay, so let's compute the pooled standard deviation or variance. So pooled variance S square P. This is your pooled variance test. What is the formula for that? So this is your n1 minus 1 s1 square plus n2 minus 1, this one, n1 minus 1 s1 square, n2 minus 1 s1 square, n1 plus n2 minus 2, s1 square plus n2 minus 1 s2 square by n1 plus n2 minus 2. So let's do have computed it already. So n1 is 24, 24 minus 1 into s1 is standard deviation of the first one. So that is A, that is 4 square 16, plus n2 is 18 minus 1, second standard deviation is 3. So this is into 3 square by n1 plus n2 minus 2. So this is your 24 plus 18 minus 2. So this will be equal to 23 into 16 plus 17 into 9 by 24, 18, 42 by 40. So this will be, if you calculate it right, this will come out to be, just do a simple math, this will come out to be approximately 2.67. Okay, no, not 2.67, sorry, this will come out to be, that is the final value, this will be approximately 13. Okay, this will come out to be approximately 13. And then the test statistic says that this will be x1 bar minus x2 bar by pooled this into square root of 1 by n1 plus 1 by n2. Let's put the numbers. First mean is 91, 18, 88. So this is 91 minus 88 by, so this is s square p. So sp would be, sp is equal to square root of 13. This would be equal to, what will be square root of 13 equal to? This will be approximately equal to 3.6. Just check that again. So 3.6 into square root of 1 by n1. n1 is 24 and n1 is 24 and n2 is 18. A and B are 1 and 2. Okay, so 1 by 24 plus 1 by 18. 1 by 18. So if you calculate, this is 3 by 3.6. square root of 1 by 24 plus 1 by 18. If you compute this finally, this will come out to be approximately, this will be 2.67. Okay, do the maths. This is simple, you can do it. The main thing is idea. Okay, I won't do the maths. So, and what is my degrees of freedom here in the pooled variance test? N1 plus N2 minus 2, this is 24 plus 18 minus 2, that is equal to 40. So let's compute the T alpha. So alpha, let it be again 0.05 or 5%. This will be equal to, what will be, so what all values I need? I need that this is my 0.05 and I need my degrees of freedom. My degrees of freedom is equal to 40. So let's check the table again and find out what is the degrees of freedom in this table itself. So this is your same table, T.95, that is 0.05 is my one tail test. And then here you go just down in this column, here, here in this value, okay, and go to 40. So if see 40, and if I keep traveling in the 0.05, this is 0.05, this one column, and come to 40, 40, 40, 40. This will be 1.684. If you see the value, I'll highlight this, 1.684. Okay, so this will be equal to, see the table, okay, 1.684. So if you see again, quickly plot it. Initially, I'll advise you to keep plotting it so that you get an idea. So this is symmetric, and your 0 is here. T alpha is equal to 1.684, and my T observed, this is your T observed, right? My T observed is clearly 2.67, okay, 1 unit ahead. So this was my rejection region, or this is my, where alpha is equal to 5%, and this is your P value, which is definitely, this is for probability of observing T greater than or equal to T observed. So this value is definitely less than the critical value, or the area under the curve is less than 5%. So we reject null hypothesis finally and accept alternate hypothesis. And what does the alternate hypothesis say? That the new algo is significantly better than old algo. The accuracy, the new algo's accuracy, in terms of accuracy. Okay, that's what we are comparing. That's what was our alternate hypothesis. Accuracy of A is greater than B. So this is your, it is significantly higher than this because we have rejected the null hypothesis, and the new model is performing better. I hope this is clear. So let's do a quick revision. So we understood what is t-test. T-test is required for n less than 30 and when the sample standard deviation or population standard deviation is unknown, okay, for small size samples. And this uses student's t distribution. Student's t distribution is t distribution, and the scientist name was William Gossett, but when he published the paper, he published it under the name or a pseudonym student. That's where this name comes from, student's t distribution. Okay, this is the, what is the t distribution like? It's a generalized normal distribution or Gaussian distribution with for small sample size where n is less than 30 and unknown standard deviation or unknown variance. Here the property is that the tails are thicker than a normal distribution, okay, and this is zero centered and the tails are thicker, and since it is a very small sample, the variability is unknown, so we go via the, we include one more thing to understand the variability, to capture the variability of the data. Okay, so that is captured by degrees of freedom. So we understood what is degrees of freedom here, and then we saw what is the t distribution. So if n tends to infinity, your t distribution will tend to normal distribution or Gaussian distribution. Okay, and then we saw types of t-test: one sample mean t-test, two sample mean t-test. One sample mean t-test is used for sample mean, okay, to test whether the sample mean differs from the hypothesized or some known value. And two sample t-test is used to compare two independent samples, two independent group means. Okay, and third is paired t-test, where I compare related sample, that is before and after some effect. And then we saw examples of one sample t-test. The test statistic is x minus mu by s by root n. So everywhere you will see this format, that the mean is a difference of mean divided by some form of standard deviation. So this is your one sample t-test. Within two sample t-test, okay, then we saw two sample t, within them there are two types, okay, two subtypes. One is for when whether the two samples have unequal variance, then the formula is different, okay, and the degrees of freedom is calculated in different way. It is calculated using Welch formula, okay. And then we saw the equal variance, where both the variance of both the samples independent groups are equal, okay. And then we have the pooled, where we have the notion of pooled standard deviation or pooled variance, and that's what we use. This if you see this one, the formula here, the pooled standard deviation, or the pooled variance, or and the independent variance, the unequal variance. So this formula are almost same, only the calculation of pooled variance is extra, and the calculation of degrees of freedom is different in both of them, but the test statistic formula is almost same, okay. And then we saw a problem to solve this, and we understood, okay. And then we followed all the steps for null hypothesis to understand this, for the hypothesis testing to understand this. So slowly we'll do more problems on hypothesis testing, and you will get more hang of it, and you will get better at it, okay. On this note, let's end this video. Thanks for watching this video. Have a great day, and bye for now.